make sure my slides are working here. All right. So again, my name is Holland Gistelli. I'm the Education Program Coordinator at Pepperwood. And Pepperwood is a nonprofit organization, and our mission is to inspire conservation through science. And I'd like to take a moment, even though we are not at Pepperwood yet, I would like to take a moment to acknowledge that Pepperwood Preserve sits within the traditional homeland of the Wapo people, and we respect and honor past, present, and future generations of Wapo and their continued connection to this land. We are grateful for the opportunity to gather in this beautiful place, and we give our respect to its first inhabitants. And this was authored by Clint McKay, who is on our Native Advisory Council, as well as is our Indigenous Education Coordinator. So the preserve itself is 3,200 acres. It's home to over 900 species of plants and animals. So those of you who will be joining us on Saturday will get to witness some of this in person. So we're looking forward to that. Our founders are Herb and Jane Dwight, and we've named the Dwight Center for Conservation Science after them, and that's our main building on site where our offices and classroom space is. So that's where we'll see you on Saturday. And while we are preserved, we're more than just a place. We also are an organization of people who do a wide range of work. We can kind of bucket our work into three categories. We conduct research on climate, wildlife, plants, and we use that research to then inform our community and share best practices with the wider world around us, and to better steward our land. We have education programs such as this one, so community, open to the public community events. We also serve local elementary school students with a field trip science program. We have a summer teen program, and we partner with local colleges as well. So opportunities for lifelong learners of all ages. And last, but certainly not least, is community. So as I mentioned, we work closely with our community through education and research. And we invite our volunteers to come on site and help support us with our work. And we are ever grateful for our donors and volunteers. So thanks for being part of our community here today. And I would now love to introduce Rebecca. So Rebecca Perlroth is our instructor tonight, and Rebecca has spent the past 20 years studying and teaching the geology of California, and currently teaches geology at Santa Rosa Junior College. She earned her BS from Tulane University and her MS from UCLA. And Rebecca has taught geology classes in partnership with Pepperwood for many years, so we're thrilled to have her back with us again. And now I'm going to actually just stop sharing my screen for a minute here. And now you can all see each other in the room. And I'll pass it over to Rebecca. And as I mentioned, at any time you can ask questions during Rebecca's presentation, and we can just address those as we go, so you don't have to wait till the end.
Yes, please. I encourage you all to ask questions. This is only my second time doing a live Zoom presentation, believe it or not, in the last 2 years. Most of what I do has been asynchronous lectures, leaving it up to my students to log in and view sort of pre-recorded videos. So I welcome your feedback and the interaction that I very much lack right now in the current climate. So please ask anything you have as we're going on. We do have a lot to cover. As you might realize, geology, particularly here in California, is a really involved and detailed topic. And so let's get started. I'm particularly looking forward to the field trip on Saturday. Okay, where is it? I can't even see my own screen. You guys are in my view. There we go. So my plan for tonight, just so you all can kind of see where we're going, is the administrative stuff that Holland just went over for us. We're going to do my geology lecture, and then the plan, of course, is to discuss what we're going to be doing on Saturday, so you're all prepared and extra super duper excited to meet me there on Saturday morning. So I do like to start with something funny. Someone sent me this the other day. I have a 4-year-old, so it's particularly appropriate. So anyway, there is that. I get a kick out of stuff like this. I don't know. It just makes me giggle. So there we go. All right. So we're going to start by talking about the history of modern geology and understanding Earth processes. So much of this is probably material that you've heard or seen before, but I'm just going to run through it really quickly. And we will see if you guys have any questions by the time we are done. So the study of modern geology really kind of began in the 1600s, and I'm not going to talk about how all that craziness began, but really it was in around 1900 when people really started looking at and studying maps. And these maps allow people to view, obviously, the entire world as a whole. And someone made a very interesting observation that I'm sure I didn't make when I was a intro geology student, or when I was in, learning about geography and topography when I was in school. But a man by the name of Alfred Wegener, who was a German meteorologist, loved maps, noticed that the coasts, see what's happening here. My slide won't move forward. Oh, there we go. That the coasts of the east coast of North and South America mimicked in shape the west coast of Europe and Africa, and came up with this idea that these things were kind of smashed together and put all together and had somehow moved and separated and moved to their present locations. And this idea has come to be known as continental drift. It's something most people have heard of. His evidence, of course, when people asked, was this amazing fit of the continents. They fit together like pieces of a puzzle where, the outy bits of one match the inny bits of the other. So you can really see how startling this alignment is between these land masses. In addition to rock evidence across these continents, when they were put back together, we have fossil evidence, which really was kind of the nail in the coffin when people suddenly said, oh, hey, maybe the continents really have drifted, because otherwise, how else would any of this make any sense? And so when we look at the continents the way Wegener had envisioned them, the places where these fossils have been found suddenly line up, and whole mountain ranges line up across these massive ocean basins. So this idea of continental drift has sort of taken on a life of its own here, where we have Pangaea, which is the name of this supercontinent that Wegener envisioned. This is a modern artist's reconstruction. This is actually Wegener's drawing of Pangaea, how he kind of fit all the continents back together. Pan means all and Gea means earth. So of course, this was all of the what they knew of as the earth, right? Which was the land, all put back together. If you can envision the globe with all the continents in one place, the entire rest of the globe was water, which I think is just an amazing thought, that there's like this one island and the entire rest of the globe is covered by oceans, which is pretty startling. But his idea didn't really hold water. People didn't really accept this idea until new lines of evidence really came around. And it wasn't until the 1960s that people started saying, hey, wait a second, let's look at this in a little more detail. This really does kind of make sense. And with a little bit of understanding about the interior of the earth, we now, of course, realize that the surface is moving. And we've now sort of reinvented Wegener's idea of continental drift and turned it into the theory of plate tectonics. So I have a bunch of these little animations in here, so bear with me. They're usually only a few seconds, but this is, as you can see, from Pangaea to the modern continents. So the way Wegener envisioned it and how the continents have moved over time. So whole ocean basins have have literally opened and formed as the continents have moved and spread. Some ocean basins have gotten narrower and even closed, as in, as in the case of where India, we'll watch that again, why not, right? Where India has moved northward. So this little landmass right here is India, and you'll see it moving northward ultimately to collide with Asia. So we really see that the continents are in fact drifting. But it's a little more complicated than that. It's not that the continents are sliding across the ocean floor, which is what Wegener had kind of proposed. Instead, it's that the surface of the Earth, of course, which that top layer of the Earth that we refer to as the lithosphere is actually divided into these individual pieces. And the pieces are moving around the surface of the Earth in different directions. So of course, in some places they're bumping into each other or separating from each other. And those are the processes that we see. The really interesting stuff in geology, most of it really happens at these plate boundaries, where we have volcanoes and earthquakes and tsunamis and landslides, and all of these things are typically happening at the boundaries or the joining points of these individual tectonic plates.
No. I have alt. Well then, space.
All right, so we're going to talk then about, so I'm just going to, that was my really brief introduction to the history of plate tectonics. Now, moving forward with plate tectonic theory, let's talk about how the plates interact. And this is going to make a lot of sense when we start talking about California, because California really is geologically fascinating and diverse. So let's talk first about a type of plate margin or plate boundary called a divergent plate boundary. This is where two plates are moving in opposite directions away from one another. So very simply, this is kind of a step 1, step 2, step 3 type of diagram. We have movement happening in the layer below the lithosphere, which is basically the mantle. And that flow within the mantle of the Earth causes or drags apart this upper layer of lithosphere. You can see the arrows representing the direction that the lithosphere is moving. And as you stretch something, it actually gets really thin in the middle. Geologists like to use food as an analogy, and this is one place where we talk about candy bars. We talk a lot about Snickers bars. So, you know, if you have your Snickers bar and you start pulling on either side of the Snickers bar, right, what's going to happen? You're going to start pulling that apart. It's going to cause the chocolate to start fracturing. And then you have your nougat and your caramel inside, and that starts to get thinner and it starts to get stretched and stretched. And that's what we're looking at here. This is that the crust is being thinned out. It's being pushed up from below and it's being dropped down from above as a result of that lateral spreading. So we end up producing something called a rift valley. Just as an example, the East African Rift Valley is one of these locations where we have this process happening in its earliest phases. After some time, of course, when you pull your Snickers bar apart, ultimately it's going to break and you're going to end up with two separate pieces of Snickers bar. And when that happens, material from the mantle of the Earth can actually rise up through these fractures and start erupting out onto the surface. And it cools and it hardens and it solidifies on the surface in contact with the cool surface of the Earth. At some point, the crust is thin enough that it actually is below sea level. So seawater will rush in and we end up with this so-called linear seaway. A couple examples of that phase of divergence would be the Red Sea between the Arabian Peninsula and Africa. Also the Gulf of California between Baja and mainland Mexico. These long, thin, really narrow ocean basins are at this phase of divergence. And of course, as the continents get farther and farther and farther away, that ocean basin simply widens over time. And we end up having this new material that is produced in between, represented here by this gray with the stripes on it. This is oceanic floor. So the rocks of the ocean floor that are made of basalt. They're derived from the mantle of the Earth, and they are very different than the rocks that make up the continental land masses. So that, in a nutshell, is divergence. So here's a little small animation showing divergence. So the heat rises and starts spreading laterally, dragging that lithosphere with it. Ultimately, a small fracture develops and the mantle can rise up into here. And all this stuff that has the stripes on it is new ocean floor that's being produced as the two sides are separating. This central feature where the mantle material intersects the surface of the earth is called a mid-ocean ridge, and we're going to see that and talk more about it as we are going through. Everyone with me? Everybody's good? Okay, good. A few people I can see gave me a thumbs up. I like that. Okay, so when we look at the ocean floor, this is a satellite image, or I guess it's been compiled from satellite images, just showing you, of course, the continents, and everything in blue is under the oceans. This sort of grayish feature that's imposed on the oceans here is this system of mid-ocean ridges. Supposedly, it's the longest mountain range on Earth at over 47,000 miles long because it loops around the Earth like the seam on a baseball. So you can see this coming over, and this point right here on the left side of the map merges with this point over here. So you can see that it just loops around the whole Earth. And as I mentioned, the Red Sea is an example of that very early phase, that linear sea phase, that long linear ocean basin phase. So that is the divergent plate boundary. Anywhere you see this, there is an ocean basin. All divergent boundaries exist in oceans. All right, so then that leads us to a more complicated type of plate interaction called a convergent plate boundary, where plates are moving towards one another. And there are a couple of different types of convergent plate boundaries, but we're really only going to talk about one of them that's relevant to our story here in California. And this is what we call a subduction zone. To subduct means to dive down underneath. So here we have an oceanic plate colliding with a continental plate. And so oceanic plates are thinner than continental plates, and because they came from the mantle, as we just described how ocean floor is formed from a mantle material rising and cooling, that material came from the mantle, and so it's dense and it's heavy, and so it can sink back into the mantle underneath the continental crust. So where oceanic lithosphere is involved, it is always the oceanic lithosphere that dives down and subducts under the continental landmass. So we have a couple of important features here. This deep point where the two intersect, it kind of forms a V, is called a deep ocean trench. The deepest places on the floors of the ocean are these deep ocean trenches, the Marianas Trench being an example. We always have, as this oceanic plate dives down, we always have melting that occurs just above it at a depth of about 140 or so kilometers, around 80 miles down. There's melting that occurs. And that molten rock is less dense, so it rises up towards the surface of the earth, and it will pool in a few places on its way, ultimately making its way to the surface to erupt out in the form of a chain of volcanoes that we call a volcanic arc. So all subduction zones have a trench where the two plates meet. That's the actual plate boundary, and they all have this molten rock rising to the surface, therefore a volcanic arc parallel to this deep ocean trench. There's a couple other features I want you to take away from this diagram, and I'm going to add them one by one. This feature here is called a four-arc basin. Big name, don't get bogged down by the name. A basin is just a low spot, like your sink, right, is a basin. So that's what that means. And four-arc just means it's before the arc, okay? So it's just between the trench and the volcanic arc is our four-arc basin. So we have our four-arc basin here. It's a place that collects sediment, basically runoff rivers, bring sediment down and dump it into the ocean. We have volcanic material that gets dumped in and accumulated here in the four-arc basin. Last feature I want you to take away from this diagram is this concept of an accretionary wedge. We're going to talk more about these features later, but want you to know where they're located. So the accretionary wedge is this little yellow mass right here that is, again, parallel to the trench, parallel to the four-arc basin, parallel to the volcanic arc. But it is material that gets scraped off the subducting plate. So you can envision that there's a lot of friction between these two plates. And as one plate is diving down, anything that's on that oceanic plate sediment, dead critters, organic material, whatever's there gets scraped off by that frictional force, the two plates rubbing against each other. So we end up with this kind of pile of debris. It's a pile of sediment that is from the subducting plate, but it is now part of the continental plate. So it becomes part of the non-subducting plate. Okay, everyone still with me? Okay, I'm gonna thumbs up you. Good. So convergence, I couldn't find a quiet one. This one is narrated. It's like a minute long, but it's anyway, you'll like it. It has cheesy music.
Oh. Yeah,
In the subduction zone, the thinner yet denser oceanic plate dives beneath the continental plate. The continental plate is locked to the subducting plate by immense friction along the shallow portion of a vast sloping fault surface. GPS data from many subduction zones show that the friction indeed causes the leading edge of the overlying plate to be forced backwards. During subduction, the thin layer on top of the oceanic plate is scraped off and forms a wedge at the front of the continental plate.
That's your accretionary wedge.
The continental plate
Good
deforms.
question.
Plates can lock for hundreds of years until frictional stress is overcome in a process called elastic rebound. This can produce magnitude 9 great
No, not your fault. I just don't understand why I can't ask the question.
tsunamis occur when the ground beneath.
Millions of years, 100,000 years, how long are we talking?
We've got a question.
Yes.
Yes. How long are we talking? A million years, 100,000 years? How
Till
long?
for what process specifically?
For the seduction. We talking, how long did this take?
Oh, subduction continues for millions and millions of years.
Okay,
So a plate boundary can stay active for hundreds of years. So
okay,
this process,
so this seduction took millions of years, yes? That's what you're saying, yes?
that is what I'm saying. So
Okay, okay.
So this process of the accretionary wedge building up, the friction between the two plates building up,
Yeah.
can be going on for, like I said, hundreds of millions of years. Now, the frictional force here that they were talking about, how the plate gets kind of bowed upwards and then it has all this elastic rebound. That process typically releases stress I would say every 100 to few hundred years, and that's what produces these so-called mega thrust earthquakes that have happened in Japan, off the coast of Chile, in New Zealand. They've actually happened off the coast of Alaska and Western United States as well. So that process of stress building up such that we're producing these massive earthquakes, we're talking like 8+ magnitude earthquakes.
Okay, so I've planted a lot of vineyards on the Sonoma coast, and most of the rock I find out there is metamorphic rock. From Lake Sonoma to the very end, everything I planted is either on greenstone or schist or greywacke. It's mostly metamorphic rock. Why?
Yeah.
Why is that?
Well, we're going to talk all about that if you give me a little bit, but in a nutshell, you live on an accretionary wedge.
Yes.
So you live on this deposit of material that got scraped off the ocean floor. And that process of accretion adds a lot of friction, adds a lot of heat and pressure. So those rocks, even if they weren't metamorphic before, and some of them were, if they weren't metamorphic before, they get metamorphosed by the heat and pressure from the that accretion process.
Okay. So there's a vineyard above Lake Sonoma that has a boulder of greenstone the size of I mean, it's huge, and schist that comes 30, 40 feet out of the ground.
Yeah.
I mean, it's all metamorphic rock. So even most of Alexander Valley is metamorphic rock. So you're saying this all came from here, from this wedge?
Yes, that's what I'm saying.
Okay.
And I can give you a more detailed answer as we're going through, because this is just, this intro part is just like the broad. I'm going to switch to talk specifically about California and Sonoma County specifically. And so hopefully fill in the gaps to all of this. And then if I haven't answered your question, ask me again, just so you know, the first rock we're going to look at on Saturday is a massive metamorphic boulder that I don't know, it's got to be
What?
30 or 40 feet tall. And
What is it? Is it greenstone or schist or what is it?
Blue schist.
Blue schist. Okay. Yeah. Yeah.
And we're gonna see chert, we're gonna see volcanic rocks. We're gonna see,
chert's sedimentary, isn't it?
it has been metamorphosed, but yes,
but it's sedimentary rock to begin with. Yes.
It's just sedimentary rock. No, but much of the stuff we have here in the wedge is because of that accretionary process.
Yeah. So I'm a soil scientist, PhD. I know a lot about geology. I've planted vineyards from there, so I'm trying to learn here. Sorry.
Yeah. So let me keep going and we'll see if I have answered any of your questions. If you do have specific, like how does this particular rock type form, that's a totally different thing that is much more detailed than what I put together today, but I'm happy to try to answer.
I would like to know where chert came from.
Okay, we're going to talk about chert.
Thank you.
For sure. And I'll spend even more time talking about it on Saturday because we're going to be standing on it and I can give you some really cool details about that chert, not just like chert in general. Okay.
Rebecca, I have a quick clarifying question that came up in the chat.
Okay.
So the accretionary wedge stays floating and is not dragged under the continental crust?
That is correct. So again, this is obviously oversimplified, but there is this layer on top of the oceans, and the farther the ocean crust gets from the mid-ocean ridge, the more sediment piles up on it because there's just more time for sediment to be brought down from the land. And so some of this material undoubtedly does get dragged under here, but the stuff that's plucked off ultimately does get accreted onto here. So it came from here, from the subducting plate, and doesn't get subducted.
Gotcha. And so then it kind of becomes part of the continental plate.
It does. It ultimately tacks onto the edge of the continental plate.
And is this a continual process? Is the subduction going on right now?
Yes. No. Yes and no. It's not happening here in our part of California anymore, but it is happening in Northern California, Oregon, and Washington, and many other places around the world. South America, Japan, Alaska.
But it's very minimal. It's very slow.
Sure, it's slow. Plates are only moving, they say, the speed that your fingernails grow. So we're looking at like 1 to 10 centimeters or 1 to 15 centimeters a year. So it's a really overall pretty slow process. So it's not something you can observe, which is why we don't have earthquakes every year. There's not enough movement to create a large earthquake every year, but there's such minimal movement in any year that stress can accumulate along this plate boundary. That frictional force holds these rocks together so that it could be, in some cases, 100 years or 200 years or 300 or 400 years of stress, meaning, say it's 10 centimeters a year. Now we're talking 400 years worth of 10 centimeters of movement that's accumulated on that plate boundary. So when it slips, it really moves. The earthquake, the 2004 Indonesia earthquake that generated that massive tsunami in Sumatra there, that hit, Sri Lanka and all those places, within like 2 minutes, that entire plate boundary had slipped and jumped 60 feet. And an 800-kilometer long section of that plate boundary jumped 60 feet. So that's a huge amount of ocean water that gets displaced, which is why tsunamis are generated. It's like this jumping forward 60 feet. Where's this water going to go? Can't go anywhere. It just gets pushed out of the way. And that generates a huge wave, which then radiates outwards and wipes out coastal communities in every direction. That was uplifting. All right. Any other questions before we move on? All right. So the reason that this whole thing was important is because that whole thing we just talked about is really a cross-section of California. And we're going to talk more about the history of California and how this is particularly relevant. But there was, past tense, an oceanic plate subducting beneath the coast of North America. It formed an accretionary wedge. It had a four-arc basin. It had a volcanic arc. Those volcanoes have eroded away, leaving us those magma chambers, the sort of plumbing system underneath the volcanoes. That is represented by the Sierra Nevada mountains that we see. In the four-arc basin is the low-lying flat sedimentary basin that we call the Central Valley or the Great Valley. And then the accretionary wedge is the Coast Range. So if you live on the accretionary wedge, which if you live here in the Coast Range in Sonoma County, you live on an accretionary wedge, unless you live out in like on Bodega Head or Wallala, or I mean, there are Point Reyes, or a few places here that are not on the accretionary wedge, and we'll talk about all that also. But what we were just talking about is literally the history of California. All right, the third and final type of plate boundary are called transform plate boundaries. And these are places where plates are sliding horizontally past each other. Nothing goes up, nothing goes down. There's no land that gets created, and there's no land that gets, recycled or returned back into the mantle. We just have two blocks of the Earth's lithosphere sliding horizontally past one another. These exist because our planet is a sphere. All right. So in a nutshell, they exist as offsets to the mid-ocean ridge. So these are these segments of divergent plate boundary where, again, two plates are separating. But because the Earth is a sphere, these divergent boundaries cannot be just perfectly straight lines. We have the axis or the crest of the mid-ocean ridge, we have this offset, and then the mid-ocean ridge continues. And then there's another offset and the mid-ocean ridge continues. So these green arrows represent the motion of the plates, meaning everything on the right side of this diagram is heading off to the right. Everything on the left side of the diagram is heading off to the left. So out here, we have what's referred to as a fracture zone. There is a fracture, or the two sides were formed differently, but they're moving in the same direction, although there is a crack between them. So these arrows represent the plate motion here. So out here and out here, these are called fracture zones. But where the offset occurs, the two sides are moving in opposite directions. This is our transform boundary or our transform fault. All transform boundaries exist as offsets to segments of mid-ocean ridge. So just to zoom in on that map, this is the northwest coast of Africa. This is Florida. So this is the east coast of the United States, and then down into South America here. So this dark line here represents the axis or the crest of the mid-ocean ridge. And all of these lines that cut across are these fracture zones. Notice that there are places where the axis of the mid-ocean ridge jumps. And all this out here is part of the fracture zone, but just in the middle here, that is the transform boundary or the transform fault, just this little segment, this teeny little segment right here. You can see all the places where these mid-ocean ridge segments get offset from one another. Here's actually quite a large transform offset from where the ridge is here to down where the ridge is here. So this is a big one. So all of them exist as this offsets to these mid-ocean ridges. It gets interesting where these things cross land. I mean, there are thousands upon thousands of these things in the ocean basin where nobody interacts with them or sees them. But where these mid-ocean ridges cross land and where these transform faults cross land, like here, that's where the really interesting stuff starts to happen. So just very, very simply, features on the surface of the Earth become displaced as these plate boundaries slide. That friction produces earthquakes, as we well know, and features on the surface of the Earth become offset from one another. All right. So to give you guys an example, this is the San Andreas Fault showing you an offset that happened in 1906 as a result of the San Francisco earthquake. I'm not exactly sure where this is, but it's supposedly somewhere near Bolinas. And this, of course, was taken in 1906 as a result of the earthquake. This is about 8.5 feet of horizontal offset. This is not the maximum that was recorded during that earthquake. The maximum I've heard is 21 feet. Think about that. This earthquake lasted for 50 seconds and blocks of crust moved past each other 21 feet in some locations. In this location, only 8.5 feet. So the trace of the San Andreas Fault runs right through here, displacing this fence. So it's very nice to have these nice straight human-made features, roads and things, because they very easily exhibit this offset. All right, one of the other things we talk about with regards to transform boundaries is the so-called sense of motion. So depending upon whether a mid-ocean ridge is offset one direction or the other direction, right? Those two things are the same, but they're different. We can refer to, or it implies, a different direction of stress application. So this guy over here on the left-hand side, oddly, is what we refer to as a right lateral strike slip fault. And I know, so strike slip fault, by the way, means a transform fault. So the strike slip is synonymous with a transform fault. So look at how the road here in this case has been displaced or offset along the fault, which is of course the fracture between the two blocks. So the way we determine if something is right lateral, or on the right side of the diagram, they're showing you left lateral, is to pick one side of the fault. So say you're in the red car, okay, and you're looking across the fault, which way has the other side of the fault moved relative to you, right? I think you'll see that the road has actually moved to your right, okay? So it doesn't matter which perspective you are. If you're in the blue car and you look across the fault, it's still moved to your right. So that makes this a right lateral fault. Likewise, down here, if you're in the red car and you look across, the other side has moved to your left. Does that make sense? So again, this is just trying to look at the dynamics of these strike slip or transform faults, of course, relevant to California. So this is the San Andreas Fault. And I want you to determine for yourself the sense of motion. In case you're unclear, this is a stream channel coming out from the upper left towards the lower right of the picture. And that line cutting across, this guy right here, is the fault. This is the San Andreas Fault in Central California. What is the sense of motion? In case you're not sure, remember that you pick one side, that's you, you're happy. You look across the fault at the other side. Which way did the other side move relative to you?
Right.
Anybody said right, you are correct. The San Andreas Fault is a right lateral fault. And that means from the very north to the very south, it's all right lateral. You can't have part of the same fault that's right lateral and part of it that's left lateral. It's either all left or all right. And in the case of the San Andreas, it's always a right lateral fault. All right, so California really is a tectonic trifecta. So what that means is we have all three types of plate boundaries within the state of California. And I think that makes California super duper spectacular. It just happens to be where they drew the state boundaries, but we have a little bit of everything right here. And that makes us extremely geologically diverse and also very potentially dangerous. So we of course have in our northern extent up here, we have the Juan de Fuca plate. This red line here represents a mid-ocean ridge or a divergent plate boundary. So this plate is it's formed here at the mid-ocean ridge. You can see these arrows represent the divergence. It cruises along the ocean floor and actually sinks down or subducts underneath the coast of North America. So this dark line right here represents a subduction zone. And that is why we have Mount Lassen, Mount Shasta, all the Oregon volcanoes, Mount St. Helens, Mount Rainier up in Washington and on into Canada. So we have a subduction zone up here. We of course have the San Andreas Fault, which is our very own transform fault running right through the state here. And down here in the Gulf of California, which actually sort of extends up here into this little triangle of California called the Salton Trough, but this area is stretching apart and it is unzipping. So it is turning into a divergent plate boundary. As I mentioned, the Gulf of California is at that linear sea phase where it's a long, thin ocean basin. So very interestingly and very dangerously, up here is the sort of cross section of this area of Northern California. We have the mid-ocean ridge segment right here, which is this guy right here. We have another transform offset in this area here, which is represented by this transform offset right here. And that plate is formed, cruises along the ocean floor for a very short distance, and then dives down underneath the northern portion of California, creating an accretionary wedge, causing melting, which causes the volcanic arc and the formation of those volcanoes. So California really is a pretty neat geological place to be. It's what gives us our topography. It's what gives us our microclimates. It's what gives us all of these interesting, soil types and all of this kind of stuff. So just to be clear, the San Andreas Fault is the plate boundary between the Pacific Plate and the North American Plate. The Pacific Plate underlies the Pacific Ocean, and the North American Plate contains North America plus the half of the Atlantic Ocean, but separating us from the north coast of Africa and the Europe. All right. How's everybody doing? Everyone good? You're happy? Any questions? I know there's a lot.
I just have a question. On the Fuca Fault, there are active volcanoes on the Juan de Fuca Plate?
No.
Right?
So
No.
the Juan de Fuca Plate is an oceanic plate. It has no land on it whatsoever.
There's no movement on that plate, on that fault? Or
Well, what fault are you referring to? This
fault.
The Cascadia subduction
This
zone.
fault, right? Isn't that a fault right there? Or is that
It
not?
is. It's a subduction zone.
Oh, it's a subduction.
It is a subduction zone, and it actually has been locked for 300 plus years and is sort of overdue for its next large earthquake. The last earthquake was in 1701, and they think it was like a magnitude 9.3 or 9.4, which is massive. I mean, almost on par with the largest earthquake we've ever experienced. And the only reason they know that, because it was so long ago, is because a tsunami hit and wiped out Japan. So it generates
tsunami from the Juan de Fuca hit Japan?
Absolutely. Well, the tsunami from Japan hit California.
Well, yeah.
Millions of dollars of damage to the Santa Cruz Harbor. Crescent City was nearly destroyed at one point from a big earthquake in Alaska. So these tsunami waves can travel across whole ocean basins. All right. How are we doing time-wise here? 7:45. Okay. So a brief history of California. And again, it's going to be brief on California. I'm going to spend a lot of time talking about Sonoma County because this is what's relevant to us. And in that chat, a lot of you said, you're excited, you live here, you're excited to learn what kind of stuff is around, and I really appreciate that. So tectonically speaking, the west coast of North America was a convergent boundary, specifically a subduction zone, as I mentioned, from 150 million years ago until about 25 million years ago. So basically, shortly after Pangea started breaking up, which was around 200 million years ago, North America was moving west and was sort of consuming the ocean floor underneath it. For 125 million years, that was happening. We had all of the appropriate features. We had the trench, the accretionary wedge, the forearc basin, the erupting volcanoes. We had the whole thing. So picture this as North America. The edge of North America, however, was not where our coast is. Actually, most of California didn't exist. Picture the area around Death Valley did exist, and draw a line north from there through Lake Tahoe and on north. So most of what we know as California did not exist until, very geologically speaking, very recently. So remember that the accretionary wedge is represented by the rocks of our coast range. The Fork Basin is represented by the Central Valley of California, that flat sedimentary basin. It's very, very deep and is filled with all different kinds of sediment, mostly of volcanic origin. And of course, the Sierra Nevada is represents this volcanic arc. The volcanoes have stopped erupting because subduction stopped 25 million years ago. So once there's no more subduction, there's no more melting. There's no more magma rising towards the surface. So there's no more volcanoes. Once volcanoes are not being actively built, they are being actively eroded. So these volcanoes have disappeared. And when you go to Yosemite and Lake Tahoe and you go to places in the Sierras, you are standing on solidified magma chambers. That's what granite is an intrusive igneous rock, and we'll talk about that later too. Okay, so let's look at the Coast Range. We know that the Coast Range is an ancient accretionary wedge that was formed in the trench of a subduction zone. Remember that the rocks that make up an accretionary wedge come from the ocean floor. We call this material, the deposit itself is called a mélange. It's a French word that means mixture. So when we talk about a mélange, we're talking about this accretionary wedge, this mixture of rocks that got scraped off that ocean floor. So in essence, what is a mélange? It is material scraped off the subducting plate. As I mentioned, there's a lot of friction between the non-subducting plate and the subducting plate, and any loose stuff on the subducting plate gets scraped off. We can think of this like a bulldozer. Anything that's loose and on the ground is going to get plucked off when the bulldozer blade comes by. These arrows represent sort of faults or fractures within this material that's being scraped off. In some cases, pieces of the ground itself, maybe rocks embedded in the ground, get picked up. So it's this very interesting type of deposit. It's very geologically diverse because whatever was on the ocean floor is being scraped off. So we call it various solid chunks of rock surrounded by this shale matrix. So whatever was on that ocean floor, like I said, could be organic material, could be chunks of the ocean floor itself, could be, I don't know, dead critters, could be stuff, sediment from the land, could be all different kinds of stuff surrounded by this shale, which is a very, very fine-grained sediment. Most of what lands on the deep ocean floor is shale. Our melange here in California is called the Franciscan Complex or the Franciscan Formation. It's named after the Franciscan monks. So this is a diagram. Obviously, I took a picture of somebody's illustration. This was a diagram by Tom Anderson, who's emeritus SSU geology instructor, of what sort of a generalized melange deposit would look like. And this fits well with what the question we were talking about the vineyards, finding these solid chunks of rocks like greenstone and chert and sandstone or greywacke, all these chunks that sometimes stick out of the ground because we have these random individual chunks, and what is in between them, they may or may not be touching, is this shale matrix. So they are sort of isolated blocks of solid rock of varying sizes. They could be the size of a football, they could be the size of an entire house or bigger. And then when weathering occurs, when we have rain and all these things, these rocks are very hard. So they're resistant to erosion. We actually refer to them as resistant blocks. What does erode is the shale in between them. So oftentimes we will see sort of very steep types of topography with a very thin layer of soil on top that easily landslides. We see a lot of that on Highway 101. We can see a bunch of evidence of it at Pepperwood. And we see these random blocks. Some of them are buried still, some of them stick out, and we end up having these random rock outcrops all over the place that may be made of totally different types of rock, which is really geologically weird. And you go to a place like Kansas, and you can go for hundreds of miles in any direction, and the rock type is basically exactly the same. Here, you can dig down, find the nearest rock, go to your neighbor's house and dig down. You might end up with something totally different. I mean, literally like 50 feet apart, totally different type of rock. And that's extremely geologically unique to an accretionary wedge deposit. And it's very frustrating for people here trying to dig wells, and presumably for wine people too, because different types of rock have different chemicals that leach out into the soils, and different types of grapes do well on them. Some don't do well with plants at all. Some, really do well. Some have good drainage, some have terrible drainage. So we're dealing with this intense diversity because we live on an accretionary wedge. All right, so typical scenes we might see are these nice rolling hills. Anytime you see a nice rolling hill, underneath it is a resistant block with a very thin layer of soil on top. These gullies that are in between are the shale. The shale is what erodes more quickly. So the resistant blocks underlie the hills, and the shale in between is what erodes down and creates the drainage. So this is actually a picture from Pepperwood, but you can see rolling hills. All these little things that stick up are underlain by these resistant blocks. Here we have a nice rock outcrop sticking out, another rock outcrop over here. But these things are more resistant to erosion, therefore they don't erode. Yes.
Question that has come up is, where did the shale that's in the melange come from? How old is it? Is it older than the rock chunks that are in it?
It is actually the same age as the rock chunks that are in it. It is so most of what comes from land, think about what the Russian River carries downstream, or any big river you can think of. The heavy stuff, the big rocks, usually stay on land. The sand makes it all the way to the beach. And the really, really fine, like dust-sized pieces end up getting swept by the water out into the ocean. And because the deep ocean is very calm, those little teeny tiny fine particles can settle down onto the ocean floor. And when you get layers of basically mud on the ocean floor, it turns into shale. So the shale is the most common rock actually on the surface of the planet, because 70% of the planet is covered by water. And what's being deposited on the ocean floor? Mud, and it turns into shale. So it's the same age as the other blocks of rocks in some cases. In some cases, it might be a little bit younger because the rocks formed underneath it, and then the shale is being deposited on top of it. Hope that answered your question.
Yeah, thank you.
All right. So one of the other things I wanted to point out is, again, this incredible diversity of rock type. This is a photo I took at Shell Beach. If you ever get a chance to go out there, most of you probably have been out there, but in the winter, it's especially good because there's less sand on the beach, because the waves have more energy. It strips the sand off the beach and exposes more of the rocks. But this is an outcrop here of this sort of green and like rusty red chert. You can see the nice layers here, but down here we have green rocks, blue rocks, black rocks, gray rocks, all this diversity of rocks. And this is all just stuff that's weathering out of the hills. That's one of the reasons I like the beach, is because there's not a lot of vegetation to cover the plants. So other photos, this is also from Shell Beach. We got green, gray, blue, pink, I mean, all kinds of different colors, all kind of together. And that's just what's weathering out of the local hills. This is a photo of Russian River gravels. Again, we got our blues and grays and all just different colors, different shapes, different sizes of materials. So I really, I love the diversity of the materials here. I'm very tactile. I like to just touch stuff, and I love how some of it's really heavy and some's light and some's rough and some's smooth. That's one of the things that really attracted me to geology in the first place. All right, so we've already covered this. We were a convergent margin. However, subduction stopped and transform motion began about 25 million years ago. So this is the most complicated part of what I'm going to tell you. So take what you can from it, because it is really sort of hard to follow. So they've drawn on this map the outline of, modern day California, Nevada, Oregon, Washington. And on this map, they've put the location of the subduction zone. Remember, though, that at the time that this was the subduction zone, so this was the trench, that means it was offshore. There was an entire forearc basin, and the actual plate was over here, the land. So there was no California, there was not most of Oregon and not most of Washington, because the actual edge of the continent was way over here somewhere, okay? So the plate that was subducting under North America at that time was the Farallon plate, okay? The Farallon plate was diverging from another oceanic plate called the Pacific plate. So all this time was going on. So you can see they're diverging. These are the actual, these big arrows are the actual directions that the plates are physically moving. So you can see that the Farallon plate and the North American plate are pretty much coming right at each other. And that's why there was a subduction zone. Remember, it's always the oceanic plate that does the subducting. So the Farallon plate is subducting under North America here. Now, which part of this plate boundary, right? Ultimately, the plate boundary between the Farallon plate and the Pacific plate is getting closer and closer and closer to this subduction zone, and it's gonna hit. And the part that hits first is actually this part right here. So just to clarify, because I didn't, the double line indicates a mid-ocean ridge, a segment of mid-ocean ridge. The single line represents the transform boundaries or the fracture zones that we've gone over. So the double lines, again, are the divergent zones. Now, this corner where you have mid-ocean ridge and an offset and mid-ocean ridge and a huge offset over here, this corner is moving, follow the arrow, this corner is moving like this towards California. And it intersects somewhere near present day Los Angeles. So here's what this looks like. 30 million years ago. So this probably was, let me back up. This probably is, I don't know, I'm gonna guess 100 million years ago, okay? I'm throwing those big numbers around. So that's about 100 million years ago. Now, 30 million years ago, the color is different because it's a different author, but again, the double line is the mid-ocean ridge segment. The single line is the transform boundary. The blue is the Farallon plate. The whatever color this is, tan, is the Pacific plate, and the brown is the North American plate. So that corner is just about to intersect the subduction zone. And when it does so, everywhere where the Pacific plate comes into contact with the North American plate turns into a transform boundary, not a subduction zone. And that has to do with the direction the plates are moving. So just to clarify, I'll see if I can do this well. So this is diverging here, right? So this plate was diverging like that. Remember that the North American plate is going in this direction. So when you look at the direction that the Pacific plate is moving and the direction that the North American plate are moving, they're moving in almost the same direction. Does that make sense? And as a result of that, this plate is still sort of moving to the northwest, and this plate is still kind of moving to the west like this. So there isn't that coming together or colliding that would cause a subduction zone to occur. So instead, we have this horizontal sliding. We still have, let me go back to my, wherever I was. We still have divergence and subduction down here to the south of us, and we still have divergence and subduction to the north of us. Once this corner touched North America, it basically bisected the Farallon plate. It split it into two parts. We have renamed the northern part the Juan de Fuca plate, and the southern part is the Cocos plate. So this was the birth of the Juan de Fuca plate, which is to our northwest. So now we have the San Andreas Fault here getting longer with time as more and more of the Pacific plate comes into contact with the North American plate. And this is today. About 4 million years ago, the fault itself jumped over to the east and actually grabbed a sliver of California, including Baja and LA and most of the Central Coast up through Pacifica. So that part was actually grabbed fairly recently, geologically speaking. So that's how that process proceeded. All right, so to show you what that looks like, I love this animation. This shows you basically what things would have looked like. You have your time frame over here on the right-hand side. So we're talking about a time that's roughly 38 or 40 million years ago, and it's gonna move towards now, 0 million years ago. And you'll see, so the red represents the plate boundaries, in this case between Pacific and Farallon, and in this case between Farallon and North American. And you'll see this corner right here hit California, and you'll see what happens. Or I shouldn't call it California. California didn't exist. North America. Oh, I'm sorry. Go back. Actually caused extension over here. If you've noticed Nevada getting wider, you saw it jump over and grab Baja. Do you guys want to watch that one again? It's really complicated. I love this video. So it hasn't grabbed Baja, so right there, it jumped over to the other side. And now Baja and this sliver of California are part of the Pacific Plate, and they are moving northward effectively towards Alaska. All right, any questions about that? Okay. So let's generalize the San Andreas Fault. Remember that everywhere where the Pacific Plate is touching the North American Plate is San Andreas Fault. There's that horizontal sliding. The fault has been growing longer ever since that first contact occurred about 25 million years ago. The maximum estimate of displacement or offset, so how much the fault has physically slipped across those 25 million years, is about 350 miles. So it's very significant. And that's done by matching rock units that got split and moved or offset. And then the average rate of motion is somewhere between 3.5 and 5 centimeters per year. It's not, unfortunately, an exact science. So that's about 2 to 3 inches per year. Yeah.
So question, so is Baja considered an accretionary wedge?
Baja is not. Interestingly, the backbone of Baja aligns with the Sierras. So it actually was the plumbing system for volcanoes when subduction was still happening there. So there was active volcanism happening in Baja. And since the subduction zone now is to the south of that, you know that in Mexico, they have all those volcanoes and through Costa Rica and stuff. So there's still subduction happening down there, but that was the remnant of the volcanic arc. So we're looking at the plumbing system of the volcanic arc.
Got it.
All right. All right, so the San Andreas Fault is a major feature. This is a satellite image showing you the shaded relief of basically the Western United States, but you can clearly see the San Andreas Fault because the topography changes abruptly. So faults are identified when things on one side don't match with what's on the other side. And right through here, you can see there's mountains on one side and it abruptly ends and there's flat on the other side. Here, exactly the opposite. To the west is mountains and to the east is flat desert. And you can just see the fault running north as this major scar through California. You can see it up here where Point Reyes is separated from mainland California. Up here, you can see it where the Walala Block has been separated from the rest of California. So really identifiable, even just looking at the topography. But if we look at the geology, this is what I was talking about, how they determine maximum displacement. Each of these colors on a geologic map represents a different age and rock type. And so this bright red is the Sierra Nevada, and it is largely represented by granites and rocks like that of a particular age. So anywhere you see that color, that's basically the same rock formation. So like I said, that continued down here into the peninsular ranges and on down into Baja. So that sort of shows you what was happening in Baja, and they form a nice coherent line. The faults have actually displaced it and made it discontinuous. But notice that the Sierra kind of dips over here, and then that red abruptly ends. But on the western side of the San Andreas Fault here, you see a couple of these little areas that have been sheared off of that rock unit through motion. The farthest north outcrop is there's Summon Point Rays, and this teeny little black dot right here that you can't really see is Bodega Head. That is believed to be Sierran granites from way, way, way down here near Ventura. So that massive amount of displacement has occurred along the San Andreas Fault.
So Rebecca, would you say that the San Andreas Fault essentially helped create what is now modern day California?
Oh, 100%. Yeah, California would look wholly different if all of these little pieces here were somewhere down here near Ventura, right? So the coast of California would be probably the East Bay or something like that. So yeah, all of this stuff has been moved northwards. And in fact, a lot of this stuff that's on the western side of the Sierras isn't actually accretionary wedge, right? It is old material from down here that got moved north, or it is marine deposited material. It's not actually accretionary wedge material. All this stuff that's green is accretionary wedge material. So down here, this is all accretionary wedge. Some of this stuff down here is accretionary wedge, but all the stuff that's to the west of the San Andreas Fault here was never accreted. It wasn't part of that subduction zone thing. It was brought north from way down here all the way up to where its present location is.
Cool.
All right, so most people think of a strike slip fault or a right lateral strike slip fault as looking like this. And here's the San Andreas Fault. And this is the North American plate where most of North America is. And this is the Pacific plate where the Pacific Ocean is. But it turns out it's actually way more complicated than that. There is not one line that you can go to and say, you know, I'm on the Pacific plate, I'm on the North American plate, and kind of hop back and forth. It's actually a really wide zone, and it's different widths throughout different parts of California. And some scientists would even venture to say that the entire state is the plate boundary. So really everything from the coast all the way over to Tahoe is faulted with these sort of parallel faults to the San Andreas, representing the entire fault plate boundary between North America and Pacific plate. So this leads us to where we are now. California is faulty, right? We all know that for a variety of different reasons. And yes, it probably is California's fault. But anyway, so I've highlighted in purple here the San Andreas Fault, but you can see all these other black lines are faults. And this is a simplified fault map of California. There are thousands upon thousands of faults that have been mapped in California. So to zoom in, bring that a little closer to home and bring in a map that has much more detail. So this is a map, an earthquake map, right, showing you significant earthquakes recently, but all the red lines represent what are considered to be active faults. Locally where we are, so here's Santa Rosa. This is the Healdsburg-Rogers Creek Fault. Healdsburg Fault to the north of us, Rogers Creek Fault heading down into San Pablo Bay. There's a slight offset, and everybody's heard of the Hayward Fault because it often has reasonably sized earthquakes. And this is the Calaveras Fault, and where these two faults intersect, there's some crazy stress happening. So they've had a couple of big earthquakes down here as well, south of San Jose. We all know the 1906 San Francisco earthquake was on the San Andreas Fault. And then this is the 1989 Loma Prieta earthquake, where the epicenter for that guy was down here in the Santa Cruz Mountains. But for our purposes at Pepperwood, because really this is a Pepperwood course, this is the Mayacamas fault zone, and it runs right through Pepperwood. I will show it to you on Saturday, some physical evidence for it that we can see standing in Pepperwood. Represents one of these parallel strands or sister faults to the San Andreas. We are pretty far away from the San Andreas Fault, right? San Andreas Fault is way out here, and we're, quite a bit inland. This little segment of the fault takes up some of the displacement between the two plates. So I like to think of it as, I can take two things and slide them past each other, or I can take a deck of cards and put the deck of cards on one hand and then put my hand on top of the top card. And I can slide the two. We're going to get 52 motions, right? Where each card is going to slip a little bit. Some of them slip more, some of them slip less. Some of them may not slip every single time I do my experiment. This fault is just one little segment. It's one slip between two adjacent cards. That's all it is. And it hasn't moved very much. This may seem like a lot, but not when we're talking about, the overall motion on the San Andreas. We're looking here at 17 to 20 kilometers over the last about 2.5 million years that it's been active. An average rate of motion is very low, 5 to 8 millimeters per year. So it hasn't actually had an earthquake recently at all. It's storing up its energy to give us a nice earthquake. So a friend of mine made this. This red dot represents the location of Pepperwood, just so you can see where it is. And I just wanted to show this shaded relief map so you can see where the faults are. It really is very clear where the faults are. The faults are in the valleys on either side of the valley, and then the mountains erode and fill the valleys with sediment. That's why these nice valleys are super smooth, right? This is Knights Valley, Napa Valley, Valley of the Moon. So all these valleys are represented by the location of faults. And notice that they're all parallel to each other. I mean, it's just striking to me how visibly parallel these guys are. Even the mountains up here are like perfectly parallel to each other. So you can see our topography is controlled not only by that kind of hilly, sort of rolling hills topography that describes an accretionary wedge, that Mélange deposit, but also that whole accretionary wedge deposit has been sliced a bunch of times and then slid like that deck of cards. So we're dealing with a bunch of different forces that control our topography and our geology. All right, so let's talk about the triple junction. How are we doing? Okay. I showed you this before. 30 million years ago, the Pacific plate was about to make contact with the North American plate. And when it did, it created two triple junctions. And triple junction is a location where three plates meet at one location. So we have Juan de Fuca, Pacific and North American plate to the north. The M represents the Mendocino triple junction. And down here we have Cocos plate, Pacific plate, North American plate. That R is the Rivera triple junction. We're not going to talk about that, but suffice it to say it's similar. So if you think about what's happening here, we have the Juan de Fuca plate cruising along and diving down under North America. We have transform motion between the Juan de Fuca plate and the Pacific plate, and transform motion between the Pacific plate and the North American plate. So we kind of have like, I don't know, it's kind of weird. So we have this thing where this part is still subducting, but this part is now sliding. And what we end up with is a little hole in the middle, right? Where am I? Right here, there's a little hole. That hole is a gap in the lithosphere that allows magma from the mantle to rise up and erupt out in the form of volcanoes. So as more of the Pacific plate has come into contact with the North American plate, these triple junctions have actually migrated. The Mendocino triple junction has moved north. The Rivera triple junction has migrated to the south. So Mendocino triple junction now is located off the coast of Point Arena. All right, the whole point of this is there is volcanic evidence for past volcanic activity along the San Andreas Fault, which is weird because we associate volcanoes with subduction zones, not with transform faults, right? Transform faults, we just have plates sliding horizontally past each other. So why are we having volcanic eruptions? But if you look at them down here, we have some that are 24 to 22 million years old. This is right about when North America collided with the Pacific plate right around here near LA, opened up a hole. And as we migrate to the north, as the triple junction has migrated to the north, it's getting more and more recent. So the rocks are getting younger and younger and younger. The pinnacles, by the way, is this little guy right here. That actually is attached to the Nenach. It's part of the Nenach formation. So it is sort of an anomaly, but it's on the west side of the fault. So it's moving north with the Pacific plate. These guys, 10 to 8 million years. The Berkeley Hills, 10 to 8. Sonoma and Tole volcanics, 13 3 million, and then the Clear Lake volcanics, 2 million to 10,000 years. So we have this parallel to the San Andreas and some of its sister faults, or these sort of parallel strands of the San Andreas. We have this younging of the volcanic material as we move farther and farther north, which is why we have volcanic features located here, not near any kind of subduction zone. Examples include Mount St. Helena. So this is a picture I took. It looks just like the picture Holland is in front of. But I took this picture from Roller Coaster Ridge, which we will go to on Saturday. A lot of people ask me if Mount St. Helena is a volcano. The answer is no, it is not a volcano. It kind of has that conical shape almost that, you know, may have gotten cut off or something. It is volcanic. And what that means is it's made of volcanic rocks, but it itself is not a volcano. We can talk more about that on Saturday. We have Chalk Hill in the area up there. This, somebody thought it was chalk, which is why they named it Chalk Hill. It's actually volcanic ash from the same eruptive cycle that produced Mount St. Helena. All right, and we can talk more about this too. Did I give you guys this figure? Was this part of the handout that I gave you? Okay, so this is a figure made by Terry Wright, SSU Emeritus Geology Instructor. Mount St. Helena over here on the east, and you can see the type of rocks that we're talking about. All this goofy sort of teal colored stuff is all Mélange material. This is the San Andreas Fault, where all the rocks have been ground up and mangled along the fault as a result of that frictional sliding. And then Bodega Head, which is on the western side, it is non-subducted rocks. It's not part of the Mélange. It is, in fact, as I mentioned, rocks, granitic rocks from the Sierra Nevada that have been transported north by the San Andreas Fault. And overlying all of this stuff, of course, is Sonoma volcanics. So much, much younger by millions and millions of years, deposited on top of the Mélange material. And we can talk about some of these other formations as well. The Glen Ellen Formation is river gravels, and then this guy here is just alluvium from erosion of the hills, filling in the Santa Rosa Basin here.
Is the orange all Sierra Nevada, or just?
No, this over
Sierra
here
Nevada, isn't it?
On the Bodega Head side, this is all the diorites.
But that isn't that area there.
Yeah, so
That's
this is all rocks that are in the 200 to 250 million year range. And then these are all in the 100 million year range. And then all the Sonoma volcanics, as I mentioned, are in the like 10 to 3 million year range. Most of what we see is in the 3 to 4 million year range. All right, so really quick, we have literally limited time. I just really quick wanted to talk about rock identification. We'll talk more about this on Saturday as well. So when we're out in the field, one of the things we do is we try to classify these rocks just by, you know, site. And in California, unfortunately, there are lots of possible options, but they're narrowed down to a specific set of options. We look at two specific things when we classify rocks. One is the texture, which is defined as being the size, shape, and arrangement of the grains that make up a rock. These can be minerals or fragments of other materials. And we also look at the composition. What are those components of the rock literally made of? Sometimes we talk about the chemistry, like how much silica is there, how much iron is there. And sometimes we talk about the makeup of the grains. We'll say, this is a rock made of sand, or this is a rock made of shell fragments, or something like that. So that said, this is a very simplified version of the rock cycle. I wanted to just kind of introduce this concept that all rocks are sort of transitory, and they can be changing into one another and becoming one another and breaking down at all times. The first rocks that ever formed on the earth 4 billion years ago were igneous rocks. So we are going to start there. All igneous rocks have in common that they form from solidification of molten rock. This can happen at the surface of the earth, like we're seeing in the picture, or beneath the surface. And we tend to get rocks like granite, which is a rock that cooled inside a magma chamber. So within the crust, which is why we can see the grains that make up a granite. It had a long cooling process, and the longer it takes to cool, the bigger the grains can grow. We also end up with pumice and scoria. Pumice is the light colored one that we use to shave calluses off our feet. And then there's scoria, or what is sometimes called vesicular basalt. It's a basaltic rock that has holes in it. These are produced by gases escaping during a volcanic eruption. We also, of course, get obsidian, which is another super duper common type of rock that we have around here. If we move on with the rock cycle, these rocks exposed at the surface break down into sediment, which can then become a sedimentary rock when the grains stick back together through a process called lithification. All sedimentary rocks form at the surface of the earth as a result of other rocks breaking down into smaller components. These components get deposited on top of one another in nice horizontal layers and can become lithified. This is at Stump Beach over on the coast. All right. We commonly produce rocks like sandstone. This, of course, is not here, but this is a local rock. This is wacky or gray wacky, sometimes informally called. It's a type of sandstone that forms in the deep ocean basins as a result of typically submarine landslides, which are common off the coast of California. Shale, we talked about as being the most common type of sedimentary rock, the result of mud that gets lithified and stuck together. And rocks like conglomerate, which actually have pebbles or cobbles that then stick together with some kind of cementing agent. We see all of these things locally and at Pepperwood. Chert is another one. This is interesting because it is a biochemical sedimentary rock formed from microscopic critters. They're shells. In deposit, it looks like layered rock like this. This is from the Marin Headlands. So again, not too far from home, but this formed in the deepest deep portions of the ocean and got accreted onto the west coast of North America. And that's why it's all kind of folded and mangled. It started out as nice flat lying layers that then got folded and buckled as it was being twisted and accreted onto North America. I took this picture. These are samples I've collected here in Sonoma County, all different colors of chert. So I would say 3/4 of the rocks that people bring me and they're like, what is this? My answer is de facto chert, because most of the time it's super colorful and it's what people tend to pick up, but it can come in a whole variety of colors. Black chert, for example, is flint. Red chert is jasper. And of course, we know that makes nice tools because it's so hard. It's also very hard to work with, but they're very, very robust tools. All right. Sedimentary rock can then undergo a process called metamorphism, which is a process of change. I shouldn't say that. Sedimentary rocks or igneous rocks can experience this process of metamorphism, which is a change from its original form, igneous or sedimentary, as a result of exposure to heat, pressure, or hot fluids. So these extreme conditions can cause rocks to change into something else. They look different texturally, and in some cases, they are compositionally different as well. So common rocks there are different types of schist. We will see a blue schist on Saturday. The first rock that we're going to see, these little red guys in here, are garnet crystals. So this is a garnetiferous blue schist, and we will see that on Saturday. We may find some mica schists as well. This is a actinolite schist. I have found pieces of this at Pepperwood, but they're pretty small. I found better pieces of it at the coast, but we can find that as well. These nice green radiating needles. It's really beautiful. And gneiss, we can find gneisses. That Sur series that's out to the west of the San Andreas Fault on Bodega Head, and also on Point Reyes, you can actually find pieces of Sur series 250 million year old gneisses. Also incidentally contained garnets. When you see this kind of red guy here, you're probably looking at garnets, but striped like zebras. And then everybody's favorite serpentinite, which is in fact our state rock. This is sort of classic California serpentinite, sort of mottled light green, dark green, but it has this like a waxy sheen to it, very slick and very soft. It's a hydrous rock that formed as a result of ocean floor rocks at the mid-ocean ridge interacting with hot seawater. As the magma erupted out, it heats the seawater, which then filters back into the rocks and causes a chemical alteration and actually infuses water into the crystalline structure of serpentinite. So originally started out as ocean floor rocks and has been altered by salt, water, by salt, by water, by organic material, by carbonate. There's all kinds of stuff in serpentinite. And when serpentinite weathers, starts to erode, it can fracture and then break down into asbestos. So we commonly see these veins of asbestos that grow as needles perpendicular to the veins in the rock. So that's pretty common. It's not the kind of asbestos that gives you lung cancer. So if you see it, please don't panic, but it is still asbestos, type called chrysotile asbestos. All right. That was geology in a nutshell. And I finished 1 minute. Okay.
Rebecca, does serpentine start with basalt?
It can start with basalt. It oftentimes starts with peridotite, which is the ultramafic rocks of the mantle, which are heavily enriched in iron and magnesium. So serpentinite is also heavily enriched in iron and magnesium. We can talk about that on Saturday because different types of plants grow on these so-called serpentine soils because they're not able to pick up the nutrients they need because there's so much iron and magnesium in the soil. So we can talk about that on Saturday. It's hard to find an outcrop of serpentinite. There are a few, but they're not as obvious as you might think because serpentinite is actually so soft that it breaks down really easily. We don't have any like big outcrops of serpentinite. I mean, there are a couple, but they're hard to find at Pepperwood. Sort of off the beaten path, as it were. I just wanted to give an opportunity. I know it's past time, but anyone has any questions, I'm more than happy to stay and answer them. I've put my email address on here. Any questions you think of or anything moving forward, you should feel free to email me. I can send you a PDF of this PowerPoint presentation if you want it, or any other files if you want them. Some of my animations, and there's a really good library of animations if you like those types of animations, from Tanya Atwater. She's at UC Santa Barbara. If you just search for her name, you can go to this page that just contains tons and tons of these little fun, few second long animations. And then some of the local field guides that I put on there are from Terry Wright, and some of the images. He has a website. He's now passed away, unfortunately, but terrywrightgeology.com has that cross-section diagram on it. And he has a really, really nice field guide. If you're ever headed out to Shell Beach or Bodega Head, tells you what you're looking at with photos. Walk here, look at this, check this out. And it's literally like a geologist is standing there with you, telling you about these features. So that's another really great resource for local geologic trips. That's all I got. So anyone with any questions?
Excellent.
I can answer.
I have a question. Can you hear me?
I can.
Yes.
Okay. Would you make that statement one more time? That some people would say that all of California is the boundary between the North American and the Pacific plates?
Yes.
The whole state?
Yes, I know.
It's zigzagging around from here and there.
It is. So let me go way back. There must have been a better way to do this. But so interestingly, so the line here in pink is the San Andreas Fault as we know it. Notice that it bends to the west here and then kind of heads north. It's sort of parallel down here and here, but there's this weird bend. It's interesting that the activity here along the San Andreas Fault historically seems to be decreasing. And this area of California, called the Eastern California Shear Zone, seems to be having increasing earthquake activity. So some have proposed that the San Andreas Fault, so remember, I showed you that animation, how the San Andreas Fault was to the west and it jumped and it grabbed Baja and that sliver of California. Some have suggested it's about to jump again, that the fault itself will continue from here and not have the bend. Because, this is not geodynamically like stable, right? There's this hookup like that's creating huge amounts of friction. So some have proposed that the San Andreas Fault is going to jump to this area, and head right up through Tahoe and keep heading north and then head out to sea somewhere up here. That's totally unclear what's going to happen in Oregon and Washington. But there's this kind of dead zone that is the Central Valley. There's a lot of fault activity in the west and a lot of fault activity in the east, increasing in the east. So it is possible. And I'm not talking like next year. We're talking like, 10, 15 million years from now, the San Andreas Fault could be in Eastern California on the eastern side of the Sierras.
Yeah, thanks. That's fascinating.
Rebecca, is that the Mammoth Lakes area we're talking about, where the fault is heading up towards?
Right. So the White Mountains are just to the east of Mammoth, and LVC is the Long Valley Caldera, which is basically right here. This sort of arc that's right here is the Long Valley Caldera. So Mammoth Mountain is basically right where this S is for SN. That's basically Mammoth Mountain. So yes, I mean, we're talking about cutting right through where Mammoth is.
Makes sense that there's some good hot springs out there.
Well, that area is super, when I was in college, they said that that was a hot spot. So kind of like Hawaii, like it's not near the plate boundary. There's some localized heat source. It now looks like that's actually related to something called, way too much information, something called delamination, where the crust is actually splitting from the bottom part of the lithosphere, and it's allowing magma to come in, and since the crust is so thin, just erupt out. So there's a totally different process there. Just chemically looking at the volcanic rocks, it doesn't appear to be a hotspot. So they came up with a different theory that I guess made more sense, fit the data better.
Well, that was great, Rebecca. Tons of great info.
Whirlwind of info.
Yeah, thank you so much. And thank you for the PDF, those additional resources. I know I'm going to go back and look at those again now that I've heard it described. And yeah, looking forward to just continuing to learn more on Saturday and see these things.
Asked me in a direct message, does gray wacky come primarily from basalt? No, I mean, it's sand. It's a form of sandstone, and what makes it sort of that weird grayish green color as opposed to sort of clear quartz crystals is that it's intermixed with clay. And by clay, I mean like mud-sized pieces of sediment that get intermixed with there. As I mentioned, it's associated with a turbidite deposit, which is a submarine landslide deposit where all different grain sizes get kind of tumbled together because they're all sort of flowing downhill together in this roiling mass. And then the gray wacky gets deposited and then compressed, and that's how it becomes lithified. So I do not believe that that the primary source of the gray wacky is the basalt, because the sand grains are not of basaltic origin because they're quartz rich, and then the clay particles could really be from anywhere. They're usually broken down minerals. I don't know if that answered your question.
All right, well, with that, we will say good night to you all, and thank you once again for joining us. And for those of you who will join us on Saturday, we look forward to seeing you there. Have a great night.
Absolutely.
Thank you.